Oh no, okay. uh, I don't record it, so let me redefine these two terms. As I said, in this session I'll talk about the data flow criteria. The data flow criteria is a possibility of using control flow graph to show the flow of data along the execution passes along the program by using two concepts: the definition and the use. When we store any value for a variable, we say that we defined a variable such as this statement. In this location, this statement defined x, because this, by executing this statement, the value 42 could be stored for variable x. So this is a definition location for x, and these two locations, the location 5 and location 6, are the two uses locations for variable x. Besides this, these locations also are a diff location for variable z. So the goal of data flow criteria is to ensure that values are computed and used correctly. So we focus on the definitions and uses statements in our program. As I told you, the definitions statements could be an assignment statement, could be an input statement, or parameter passing through some method calls. And use statements is obviously trivial for you when a variable contributes in some computations for defining the value of another variable. We say that the first variable is used to define the second one. So we define this term in short. If we define this definition as a location where a value for a variable is stored into memory, and we define the use as a location where a variable's value is accessed or is used to compute to some computation to from an assignment statement. Besides these two definitions, we can define the depth of any node or any edge of our data flow graph. We define the depth of node 1 as x, because all variables are defined in this location is just the variable x. There are no any definition in these nodes. So the defined variable, the only defined variable at location 1 is x. So we define the set of all variables which is defined in location 1 as a set for def of 1, def of node 1. We say def of node 1, and def of node 1 is a set which includes just a variable x. Okay, and this is defined also for def of location 5, def of location 6. These two are the same, and both of them define the variable z. It's possible in some nodes we define several variables, because as we will see soon in next section of this chapter, when we try to model a program, a block of code is considered for each node. A block of code which executed together with no branching could be considered as a node or a location. So it's possible to have more than one variable for def of one node. And the use of a node is defined as a collection of all variables which are defined at that location. For example, the use of node 5 is x, and this is same for the use of node 6. So the values given in def should reach at least one, some, or all possible uses. This box defines the main clue to create some coverage criteria, to define some data flow criteria. So the first one, the value given in def, for example, the value stored for x at this location, this definition should reach at least one use. When we want to test once this value, it's enough to test to execute a test pass such as this. When we want to test once this value, we should test just a use of that variable. So this test pass is enough to test one use. When we want to test more uses of this variable, it's enough to test this pass and to test this one. Okay. When we want to test all possible uses, we should define enough test passes to cover all uses of some variable, and possibly we should test all test passes that connect use. According to three possibilities, according to three clues, we define three types of coverage criteria according to data flow along our program. So let's go ahead and see other concepts. As you saw in the previous slide, the depth of n or depth of edge is defined by the set of variables that are defined by a node or edge. So far you have seen several control flow graphs, but none of them define an assignment and a definition statement over any edge of the control flow graph or the data flow graph. Because in our modeling, we define that a block of statements in which all of them are executed together with no branching could be a node. It creates a node or a location of our program. As we will soon see in next chapter. So our definitions in this chapter are defined for nodes, not for edges. But as I said, in some modeling or some models such as finite state machines, such as label transition systems, the definition statements are set to edge. So the depth of edge in those modeling style are usable, but in this concept we just use depth of n node, not depth of an edge. Okay, the depth of a node is defined as the set of variables that are defined by a node. Or this is the same for depth of use, because in this chapter the uses statements, all of them are located in nodes, not over edges. So the use of n is defined by the set of variables that are used by a node. And in other modeling languages, use of edge also meaningful. What is a DU pair? Depth use pair. A pair of locations such as location I and location J could be used as a DU pair if a variable v exists that in which that location I defines v and location J uses it. So a pair of locations Li and Lj such that a variable v is defined by node I and used at node J, at location J. We say that Li and Lj be a DU pair. Okay. And what is a diff clear path? A path from location I to location J could be a can be a diff clear path with respect of some variable v if v is not declared again between Li and Lj. If if v is not given another value, is not stored again new value, when v gets no new value between Li and Lj, okay, at the path which connect Li to Lj. We say that the path of Li to Lj is a diff clear because there is no new assignment for variable v between Li to Lj from corresponding path. We define the term reach. We say that location Li reached the location Lj with respect to variable v if there is a path that connects Li to Lj and there is no another definition for v. At that path, if there is a diff clear path from Li to Lj with respect to v, variable v, the diff of v at Li, we say that it reaches the use of Lj. For example, in this graph, this definition reaches this use. And also we say that this definition reaches this use again because there is a this is a diff clear path. If we have defined x at this position or at this position again, so this path could not be a diff clear path because x is already defined at some of these points. But in this graph, there is no new value for x between node 1 and node 6 according to this path. So this is a diff clear path from L1 to L6. Okay, so we say that this definition reaches this use of x. Also, this definition reaches this use via this path, via this diff clear path. This is a diff clear pass. Okay. A DU pass is a simple subpass that is diff clear for a variable v from def of v to use of v. As I said before, this is a DU pass. This is a DU pass. Diff use pass. And this is another DU pass for this use. Okay. And this notation defines the set of all DU passes from node I to node J with respect to variable v. For example, in this graph, there are two DU passes from node 1 to node 5 according to a variable x. There are two. This is one DU pass and this is another DU pass. And also we have two DU pass for this use. This is one DU pass and this is another DU pass. So for each of these nodes, DU 1 to 5 according to variable x includes a set of two DU passes. Set of two DU passes. And this is the same for node 1 and node 6 and variable x according to our example. Okay. And this notation defines the DU passes, the set of all DU passes that starts from node I to any uses of this variable at any other locations. So this defines the set of DU passes that start from NI. For example, in previous graph, we have 4 DU passes which start from node 1. In this graph, we have 4 DU passes, 2 DU pass for this use and 2 for this use. So we have 4 DU passes which started from location 1. So keep your mind these definitions. We have several definitions in this slide and we will use them in later slides. The def of n defines the set of all definitions defined in or at node n. The use of n defines all uses of all used variables in node n. The DU pair defines a pair of locations such as Li and Lj in which a variable v is defined in location I and used in location j. A dead clear path is a path from Li to Lj in which there is no new definition for variable v along the paths that connect Li to Lj, and we define the reach if there is a dead clear path from Li to Lj according to variable v, and I defined du paths, the set of du pairs from ni to nj according to variable v, and all passes or all uses that started from this, all du passes that started from location I according to some variable v. Okay, no problem. And how about the Turing in data flow graphs? We have defined the Turing of control flow graph of several Turing of several test requirements as you see, follow all du passes. All du passes defines 4 test cases in this case. 2 for this diffuse and 2 for this diffuse. All du passes between location 1 and location 6 are 2. This one and this one. And all du passes for location 1 and location 5 are 2 again. This one and this one. So we need several test passes. At least we need 4 test passes to cover all du passes. Okay. According to these three notions